Let's look at this electrical network. In the diagram, we have two potential differences, V1 and V2. We have three resistors, R1, R2, and R3. And we'd like to know the current that flows across each resistor. We're representing these currents as across the resistors, and the book represents currents as currents in loops. Those are two equally effective ways of describing this. With the currents I1, I2, and I3, we arbitrarily set the directions. So at either node A or B, we could say incoming current, I1 plus I2 plus I3, is outgoing current, which the diagram says is 0. It doesn't mean there's no current flowing out of A. That just means our setup shows no currents flowing out of A. We'll determine what's flowing in and out in the end when we finish. We could write the same equation at B. Incoming at B is 0. Outgoing at B is I1 plus I2 plus I3. So at B or at A, we get the same equation. We can construct two more equations with three variables, I1, I2, and I3, by using any of the three loops present in this diagram. And that is the upper loop, the lower loop, or the so-called outer loop. So in the upper loop, if we start at B, then we add a potential difference of V1. We subtract a potential difference of I1, R1. As we cross the resistor, we drop potential difference. And as we return to B, we cross R2 in the opposite direction of current. So we're adding potential difference I2 times R2. Now back at B. So this loop has 0 change of potential difference. One loop has no net change of potential difference. What you gain is what you lose, so that's equal to 0. If we travel on the outer loop from B, we add potential difference of V1, subtract I1, R1, add I3, R3 by the direction we've stated, and then subtract V2. So that gives a third equation with three unknowns, I1, I2, and I3. We fill in the values of R1, R2, R3, V1, and V2, and we have this system right here. Let's express this system as a matrix. So we start with the matrix, the augmented matrix, with the coefficients of I1, I2, and I3, and the constants on the right-hand side. And we start reducing. We take 4 times R1 plus R2, 4 times R1 plus R3. That produces the second matrix. And then I'm trying to produce a 1 in this second row and second column. So I'll take minus 2 times the third equation plus the second equation. So that produces minus 1, minus 6, minus 5 in the second row. And I can use that 1, that minus 1 there, first to place a 0 in the third row in the second column. 4 times that row with a minus 1 added to the row that begins with a 4. That'll create the third row of 0, minus 19, minus 19. And then minus 1 times the second row, the one that begins with minus 1, will produce 1, 6, and 5. Well, minus 19 and minus 19 in the last row mean that the third variable is equal to 1. Divide both sides by 19. And here you've achieved reduced echelon form. All 0 rows are at the bottom. All non-zero rows begin with a 1, and the leading ones are staggered. We could solve this by back substitution right here. For example, I3 is already equal to 1, and I2 plus 6 is equal to 5, so I2 must be minus 1. And if I2 is minus 1 and I3 is 1, then that leaves I1 to be equal to 0. But if we go to the last step, reduced row echelon form, all columns with leading ones are otherwise zeroed out, we see the values of I1, I2, and I3 immediately. The units in this application are amps. So we know that the currents flowing across resistor 1, resistor 2, and resistor 3 are 0, -1, and 1 with the orientations we assigned. So really I2 is moving from left to right. So we could describe this by saying there is no current flowing across I1 in this circuit. And across R2, current is flowing from A to B, 1 amp. And across R3, the current is flowing from B to A, 1 amp.